So I'll just try to come back to have slight discussion with regard to the scale concept, whatever we have earlier talked about. Okay, so let me just try to give a slight information onto the different type of or different ways of representing a scale. So we come across generally with three different methods that we are going to be having in representing your scale in the case of a map or in the case of your plan. So whenever we are talking about a plan or a map, so we have three different ways or methods by which we represent the scale. So one of such method is nothing but we call it as engineer's method. Okay, so we certainly call it as engineered scale. And in the earlier discussions, whenever we were trying to say 1 centimeter is equal to 1 meter, whenever we try to represent all the objects that we see in the field, whatever, let's say, for example, I have got a tree, I have got some house, or I have got some building. So whatever I see in the field, if I am trying to transfer onto a graphical representation, to represent it on what is called as a sheet, so which I am trying to say it's a plan or maybe it's a map. So in the process of representing all this, we try to adopt some scale, because in the field when I am trying to measure the distance between, let's say for example, I had some axis of reference which I have chosen, and with respect to this axis of reference, whatever I have chosen, let's say the chosen so and so tree is at a distance of something in this direction, or your house is at some distance in that particular direction. So from some axis of reference, you are trying to measure and locate all those particular objects by measuring those respective measurements in the field, and you are trying to transfer all those information in the form of what is called as your map. So once you are trying to represent all that particular information in the form of a map, then you are trying to scale those, because your building in the field might be of relatively, let's say, in the width direction, in the width direction of the building. Let's say it is something 30 meters. In the other direction, the dimension of the building is something 15 meters. So this 30 meters and 15 meters dimension, I have to transfer it onto your map when I am trying to represent, or maybe your plan when I am trying to represent. So we don't represent the exact dimension of the building in your map, because drawing sheet is specific limited in dimension. So what we do is we try to transfer this exact dimensions of the building by converting it with an appropriate scale, and we start representing that particular building in your map, something like this. Okay, so the building which is of dimension 30 meters by 15 meters in the field is transformed onto your drawing sheet by representing it with some certain small dimension. So the way these original dimensions are converted onto a proper scale for representing it properly on your drawing sheet or on your map. So that's such kind of scale. Let's say, for example, 1 centimeter is equal to 10 meters. If I want to indicate, or 1 centimeter is equal to 5 meters, 1 centimeter is equal to 15 meters. So such kind of scale, whatever we are trying to represent, based on which your field data is converted to be represented comfortably on your map or on your plan. So such kind of scale, let's say 1 centimeter is equal to 1 meter, or 1 centimeter is equal to 10 meters, or 1 centimeter is equal to 20 meters. So according to your requirement, the chosen scale what you are representing on that particular map, so such kind of scale is nothing but we call it as your engineered scale. Second type of second method of representing the scale is your representative fraction, which we have already talked about. Okay, so what is this representative fraction mean? So if the represented scale is nothing but 1 centimeter is equal to 10 meters, so my representative fraction, what we indicate is nothing but 1 by 1 centimeter by 10 meters. 10 meters I'll be converting into centimeters again. So the centimeters gets cancelled, which is nothing but 1 by 1000, which I can also write it as 1:1000. So 1000 units in the field is represented as 1 unit in your map. So that way of representation is nothing but we call it as your representative fraction. Okay, and the third type of representation, or third way of representation, is nothing but we call it as your graphical scale. Okay, so what does this graphical scale mean? Let's say, for example, I have my map it's a drawing sheet in which I am trying to represent all my salient features, whatever I see in the field. Let's say this is my tree, here is some house, maybe here is another house, this is how I have my road here, and some whatever information that I have with regard to that particular field in which I am carrying out my survey. So that information I am trying to transfer it onto what is called as a plan or a map. So in that plan or map, I am not going to indicate your scale like this as 1 centimeter is equal to 10 meters, as like in the case of your what we call it as your engineer scale. Okay, so what we do here is, instead of doing that as 1 centimeter is equal to 10 meters, so on the drawing sheet itself, maybe at a particular place, okay, so we try to indicate some divisions. The scale itself, we are trying to indicate it on your drawing sheet. Let's say, for example, this is some reading 0, 10, 20, 30, and on the other side, once again, some 10 divisions with least count of, let's say, each 1 centimeter or maybe, 1 mm, let's say, for example. So 1, 2, 3, 4, 5, 6, 7, 8, like I have 10 divisions to the left of your 0 marking, and to the right of it, let's say, for example, this indicates me 10 mm, 20 mm, 30 mm, and so on, 40 mm, and likewise. On the graph itself, you are representing that scale. Now, what is the purpose of doing it? Let's say, for example, in the field, I have got a building of dimension 30 meters by 15 meters, which I am trying to convert. Then what I am going to do is, this 30 meter length and 15 meter width of that building, I am trying to convert. And while conversion, let's say, for example, I am trying to consider a dimension of 1 centimeter on my drawing sheet. I want to represent it as what is called as here 5 meters, or let's say 15 meters. So 15 meters original dimension in the field, I want to transfer it as 1 centimeter. But in the process of transferring it, I will not simply measure the dimension of 1 centimeter on whatever the scale that I see here. Okay, so it's not just that the scale whatever I am going to use here is used for measuring 1 centimeter or 2 centimeter or 3 centimeter dimension. So what I'll try to do is, I'll take my dimension by placing your scale of how much you want to represent. Let's say, for example, in the length direction, I am trying to talk about 30 meters of dimension to be represented. So 30 meters after conversion onto your map, according to your chosen scale. So how many centimeters of dimension I have to indicate? Let's say, for example, I have to indicate what is called as a 2 centimeter dimension. So if I say 2 centimeter dimension, so all these dimensions, whatever I have represented on your graph sheet, let's say they are in mm. Now, 2 centimeters means, if I place my scale here and if I start measuring the required dimension, so 2 centimeters means this 10 division, another 10 division, so 20 divisions of that dimension I have to mark, and accordingly I have to represent with that respective dimension. In this length direction, 2 centimeter line is to be indicated. In the width direction, 1 centimeter dimension is to be represented. Likewise, I will be representing everything whatever I have got according to that particular dimensions what are being transferred. Now, in the later stage, now why is that this graphical scale so important means, after some period of time, what would happen is, there could be a possibility, because of change in climatic conditions, because of various other aspects existing in nature, this particular map, which was supposed to be of certain dimension, let's say the size of the sheet in which this map, whatever I am trying to talk about, okay, the size of this map, let's say it was of some standard dimension in the length direction, the size of that particular sheet in which the map representation is done, or the plan representation is done, let's say it's an A0 size drawing sheet. Okay, so it's your typical drawing sheet, whatever you use in your engineering drawing. Let's say that that size of drawing sheet I have used for drawing my map, or maybe your plan. Now, what happens is, after some period of time, maybe after a couple of years, or maybe after a couple of months, or whatever, if I find because of some changes in the climatic conditions or various atmospheric changes, might have caused either shrinkage in this map, or sometimes it could be an elongation in the map. Okay, shrinkage or elongation might have taken place in this particular map. So when do we say the shrinkage has happened? Because of, let's say for example, maybe some water has fallen on it, and upon drying, the paper might have got shrink. Or maybe because of increase in temperature, there might have been a kind of slight elongation that might have happened in that particular material. Okay, so we do not know how the wear and tear effects are going to be in that particular sheet which you have used in representing your map of that particular town or maybe of that particular village. Okay, so now if the same map has to be used in later point of time, where that particular map has undergone what is called as a shrinkage or maybe an elongation, because if it is a shrinkage, then the original dimensions, whatever you are going to get by measuring those things in your map, they are not accurate. And similarly, if there is an elongation in the map and then subsequent measurements, whatever you measure from your map and you try to understand how they are going to be in field, that is not going to be accurate. Let's say for example, the distance what I have according to this particular drawing sheet in which all the information regarding that particular town or that particular village has been indicated. Okay, now I am trying to make use of this drawing sheet or the map for understanding or for planning something. Maybe after 5-6 years in the process of my town planning, I started looking at this map. Okay, so I started looking at the map and I started understanding, okay, I had some house here during that time and another house here, where the distance between these two houses, I'll start measuring with the help of a scale. Okay, I'll try to put the scale, one end of the scale here, and I'll try to extend your scale in this direction, and I'll try to measure that particular distance between those 2 points. And after measuring it, let's say I got some value, something 1.55 centimeters is the distance what I have got, let's say for example. So once I have 1.55 centimeters, and in case if I am directly converting this with what is called as an engineer scale, let's say for example, what was my engineer scale that I was supposed to be understanding here? 1 centimeter is equal to 15 meters was the engineer scale, according to which that's the scale what I have chosen for drawing your map. So in the process of understanding 1.55 centimeter, then what becomes my original dimension in the field? So original dimension in the field is nothing but 1.55 into 15. That gives me some dimension. Okay, so that dimension, whatever I have, whether it is true or whether it is not true, or whether you have got any error in that particular dimension what you are indicating here, yes, the measurement whatever you have calculated based on the usage of your engineer scale is not going to be correct. Why is it not going to be correct? Because your map, whatever we are trying to talk about, has got a shrinkage or it has got some elongation in it. So the volume or the dimension of that particular map is not exactly the same as the original dimension of the size of that particular map. So once the dimensions are not correct, what has happened? Let's say for example, the map got shrinked. Once the map got shrinked, this so-called 1.55 centimeter dimension, now what you have measured in your map, upon conversion of this 1.55 centimeters, let's say 1.55 into 15, 24 meters. So now original dimension, if the map was not getting shrinked, the original dimension between those two houses in the field, the original dimension was 24 meters. But because of the shrinkage of the map, when I started understanding the dimension, how much is it between your reference houses in that particular map, and when I am trying to convert with the help of what is called as your engineer scale, the calculation what I am getting is not the accurate value. Okay, so in all such cases, it is very important for us to understand how to convert your data from your map in order to exactly know what is the correct dimension in the field. If I want to do that, I should not be converting it with the help of what is called as an engineer scale or what is meant by your representative fraction. So in that form, I should not be converting it. Rather, I should be converting it with the help of what is called as your graphical scale. Now, what is this graphical scale telling me? So what I am supposed to be doing now here is, I'll certainly measure this dimension in your drawing sheet. Let's say it is coming out to be 1.55 centimeter, and that 1.55 centimeter, I'll come back here. Rather, I should not say it is directly 1.55 centimeter, because the original scale I should not be reading, because this becomes my engineer scale. Okay, so you should not read this value directly. Rather, you take a scale or maybe a thread or whatever it is, try to understand from which point to which point that two buildings are apart, locate those 2 points, come back to those that particular graphical scale which is indicated on your map, then start placing that here. In the process, when I start placing it, let's say for example from here to here, that line or thread which I am trying to place is coming. Okay, then I understand that, okay, from here to here it is 10 mm, and from here to here it is some 6 mm. I repeat, this is another 6 mm. Then I can say, okay, my dimension is nothing but it is 16 mm is the distance between these two houses what I have in my sheet. And that 16 mm you can try to convert with the help of your engineer scale, and then you can subsequently get the value to be nothing but 24 meters is what is the distance between those two buildings in your original field. Now, what is that we have done? We have converted, or you have measured the dimension of at what distance these two houses in the field are existing based on whatever the scale that is represented on that map itself, the graphical scale which is represented on the map itself. Now, what is the advantage of doing so? The advantage of doing so is, when I say map got shrinked, automatically the scale which is indicated on the map also got shrinked. Okay, so once the scale on the map also got shrinked, whatever dimensions that you want to understand from the map, if they are automatically taken from your graphical scale which is there on your map, and if that dimension, let's say if I measure, I'll be getting it as 1.6 meter, if that is converted with the help of your engineer scale, so then automatically your true measurements what you had in the field you are going to obtain. So without doing that, if you are directly converting by measuring the distances, original distances at which those two buildings are apart, by measuring that original distance, if I directly convert with your engineer scale, then your issue with regard to your shrinkage that took place in the map, or maybe an elongation that took place in the map, is not going to be taken into consideration. Let's say, for example, if elongation might have happened in that map. So once the elongation has happened in the map, then the distance, whatever you are going to measure between those 2 points, those two positions of the building in the map, if I am trying to measure with the help of your scale, if I am going to measure, the original dimension when I have drawn that map was supposed to be buildings, those two buildings were supposed to be apart by a distance of 1.6 meter, but due to the elongation, what I have seen is those two buildings are no more going to be at a distance of 1.6 meter. Slightly they might have, buildings are not moving away, but as the dimension of that particular map got elongated, so those two buildings which were supposed to be like this in your previous map are now looking apart this much at a distance. So that distance at which those two buildings, if you are trying to measure, that automatically comes out to be greater than 1.6 centimeter. And if it is greater than 1.6 centimeter in the original field, according to the engineer scale, if I directly convert it, 1.65 I've got, and in the process, if I convert it, I might be getting something 26 plus or minus somewhere around 26 meters. But whereas in the original field, it is only 24 meters. So you should not directly make use of what is called as your engineer scale in the cases where you understand there is an error in your map because of what is called as a shrinkage or an elongation. So more common likely problem is your shrinkage in the case of your maps. Whenever those maps were drawn some years before, and due to various changes that took place in the climate and various other aspects, so your measurements, whatever you are going to be talking about, are not going to be really accurate at the time when you want to convert that and accordingly understand how the measurements in the field are going to be existing. So in such cases, it would be advisable to even indicate what is called as a graphical scale on your drawing sheet, so that if you have your graphical scale represented on the drawing sheet, same scale, you have to indicate the divisions on the scale also, so that you will not have any issues. Later on, whenever you want to measure some dimension in that particular map, that can be measured with the help of the same graphical scale which is represented on your sheet. So though the sheet has elongated, same scale has also got elongated. If the sheet got shrink, scale has also got shrink. So automatically your measurements, whatever you measure from your graphical scale, would certainly give you the accurate data in order to understand how your field measurements were there in that particular location. Okay. So in case if there is any shrinkage that has taken place in that particular map, so we can try to talk about certain shrinkage of map if it is happening. So we can try to talk about certain factors like shrinkage factor. Okay, whereas this shrinkage factor is nothing but we can write it as shrunk scale divided by the original scale. So what was supposed to be the original scale? Suppose original scale was supposed to be of dimension 1.6 centimeter, but my shrunk scale was showing me only a dimension of 1.55 centimeter. So my shrinkage factor, accordingly, I can try to calculate. Then what was supposed to be your correct distance between those two buildings, which I was trying to talk about? So if I want to find out what is my correct distance that I have in your map, so I can simply write it as measured distance. So what was my measured distance? Measured distance was 1.55 centimeter divided by your shrinkage factor. So if I know what is the shrinkage factor for your map which got shrink, then I can make use of that shrinkage factor, and I will try to understand how much is the distance that I am trying to get from that shrinkage map directly by measuring any objects or whatever in that particular map which got shrink. Then based on that, I can try to calculate what is your correct distance, what was supposed to be the correct distance of those two objects in the map. So once you understand what was the correct distance it was supposed to be in your map, then you can convert it according to your original dimension, or maybe that dimension itself is going to give you your original, whatever accordingly you can try to represent. Now, if you want to understand what is my, in terms of the area, if you are trying to talk about what is my correct area, if I want to find out, it's not just the dimension in only in one direction. Okay. So if I want to understand what is the correct area of that particular region, let's say, for example, I had a pond in that region, and due to the shrinkage, what happened is the area what is represented in the drawing sheet is slightly decreasing. Now, if I want to find out the correct area of that particular map, the correct area of that particular pond indicated on that map, so what I can just try to do is I can try to calculate like this. It's a measured area, whatever you have, divided by shrinkage factor whole square. Why is it whole square coming into picture? Because whenever you are talking about area is nothing but length into breadth. So in the process, if I am trying to talk about length dimension is to be corrected, width breadth dimension is also to be corrected. So it's the correct length dimension, it's the correct width dimension. So correct length dimension has got shrinkage factor in the denominator, correct width dimension has also got shrinkage factor in the denominator. So automatically, let's say your correct length is equal to L dash by shrinkage factor, correct width is B dash by shrinkage factor. What is L dash? L dash is your measured length or measured distance from your map because of the shrinkage, and B dash is nothing but measured width because of the shrinkage in your map. So if I am trying to calculate what is your correct area is nothing but L into B, which I can write it as L dash by shrinkage factor, okay, into B dash by shrinkage factor. So automatically it comes out to be L dash into B dash by shrinkage factor square. So that L dash into B dash is nothing but we call it as your measured area. So that's how you can try to convert your error dimensions into the accurate dimensions, and accordingly you can try to calculate, or you can try to locate how exactly was there was those dimensions in the field when you were when you tried to identify and map those objects in your map. Okay. And then now moving on with our next subsequent discussion. So earlier we have seen certain terms like we'll be trying to talk about carrying out the survey based on various instruments, like depending on the type of instrument. We said we will talk about what is called as your chain survey. We will call something as compass survey, or a theodolite survey, or a survey carried out based on electronic distance measurement equipment or instrument, or maybe based on total station I am carrying out my survey. So likewise, you have different instruments or tools by which you can carry out your surveying. So in the process of talking about those various instruments or whatever for carrying out your survey, what we come across is there are certain possibilities of committing errors while you are carrying out the survey. So there are all chances that you might commit certain errors while carrying out the survey. So let us try to understand what are the different sources of errors. Now, when I am trying to carry out my survey in the field, what could be the different sources for getting those errors? Okay, why do we come across with those errors while carrying out the survey in the field? So, one such kind of error could be your natural error. Now, what does this natural error mean? So, let's say, for example, I'm talking about a scale, or maybe a chain, or maybe a tape that I have for measuring some linear measurements. Let's say I have one point here, I have another point here. Let's say this is point A, this is point B, and I'm just trying to measure this distance between these 2 points. Now, when I'm trying to measure the distance between these 2 points, if you could look at this particular scale, okay, the scale what I am trying to use here is a 30 centimeters length scale. Okay, when this particular scale has been manufactured, okay, the scale, the so-called 30 centimeter scale what I am trying to look at, okay, so this 30 centimeter scale what I am trying to talk about might have got manufactured at some standard temperature. Let's say, for example, maybe some 27 degrees centigrade. So in general, this temperature 27 degrees centigrade most of the times is taken as a standard temperature in your design and in manufacturing aspects. Okay, approximately around 27 to 30. So depending on that locality climatic conditions. Let's say, for example, this is manufactured at a standard temperature of 27 degrees centigrade. But the temperature what is existing in the field when I am trying to carry out my survey, I repeat, when I am trying to carry out my survey, the temperature is something very high. Let's say, for example, it is something approximately some 45 degrees centigrade or something approaching to 50 degrees centigrade. So at that temperature of 50 degrees centigrade, whether the scale what I am trying to use here for carrying out the measurement between those 2 points A and B, or maybe a tape which I am going to use for measuring the distance between point A and B, or for a chain which I am using for measuring the distance between A and B, originally they are manufactured for a standard temperature where the length of that scale was supposed to be 30 centimeters when the standard temperature of 27 degrees centigrade is existing. But now in the field, it's not 27 degrees, rather it is nothing anywhere near to 27 degrees centigrade. So it is somewhere very high. So let's say, for example, 45 degrees centigrade or some 50 degrees centigrade is existing temperature. So because of that, what would have happened in this particular scale? The length of the scale is no more going to be 30 centimeter, rather it is going to be something higher than that of the 30 centimeter dimension. It totally depends on the thermal expansion coefficient of this particular material by which this particular scale is made. Now, if the coefficient of thermal expansion for this material is high, then what happens is the length of the scale is no more going to be exactly 30 centimeters, rather it is going to be something higher than that of your 30 centimeters. And if the length of the scale is higher than that of the 30 centimeters, and if that particular scale is used for measuring the distance between point A to point B, okay, let's say that measured distance with the help of that scale which was supposed to be 30 centimeters but not 30 centimeters, which is more than 30 centimeters, If I measure the distance between A and B, then that measured distance is not the correct distance. Let's say my measured distance, I got it as 50 centimeters. With the help of that scale in which expansion took place, same scale if I am still using it, and measuring your distance between point A and B, or same chain I am using, or same tape I am using, in which some thermal expansion took place, and if I am measuring the distance between those 2 points, that measured distance is not correct distance. Then what would have been the measured distance? Measured distance, will it be greater than that of 50 centimeters, or will it be less than that of 50 centimeters? So the measured distance, what I am trying to talk about, will be greater than that of, the actual distance. Actual distance should be greater than that of 50 centimeters, whatever you have measured with the help of that scale, in which there is an expansion that has taken place. Okay, so you have to be very careful. Likewise, sometimes when you are trying to locate the position of some point in the field, there could be an issue because of wind and various other aspects. So when you are trying to locate the position of that instrument with the help of what is called as a plumb bob. So let's say, for example, this is what we call it as a plumb bob, a thread connected with a bob at the bottom. Relatively heavier in weight. This bob is made of steel material, mild steel material. So because of the heaviness of the weight, so this bob always tends to act or show us the direction of what is called as your gravity. Your bob will always get suspended towards the direction of your gravity. Okay, so if there is a wind, let's say there is a wind what you are having while carrying out the survey. So due to the wind, what is happening is your exact position of your location, you are not able to transfer it onto the ground. And as there is a wind, the position of this point of the bob, which was supposed to be indicating me where is my station, so it is not exactly locating the position of that station. Rather, it is getting shifted to some other new point, and it is showing me the station somewhere else. So what is it indicating? It is indicating because of some natural issues, maybe due to wind, maybe due to different temperature, or maybe due to different atmospheric conditions. There are certain errors what you are coming across in your measurements, what you are trying to get while carrying out your survey in the field. So you have to be little careful. So while conducting your survey, whether you are encountering any such kind of natural errors while carrying out the survey. And next is instrument errors. So what does this instrument error mean? So here instrument error, for example, if I go back to this scale, on my scale, I have got some divisions, let's say 0 to 1 centimeter, 1 centimeter, 2 centimeter, 2 centimeter to 3 centimeter. Even in between this 1 centimeter to 2 centimeter or 2 centimeter to 3 centimeter, I have got 10 divisions indicating. So what does it tells me? I am going to measure my dimensions to an accuracy of 1 mm, which I am calling it as the least count of this particular scale. What is meant by least count? Least count is nothing but the least dimension what you can measure accurately with this particular scale. So that is what I can call it as the least count of this particular scale. Okay, let's say for example, if the least count of this scale is 1 centimeter, and when I am trying to measure the distance, let's say I am trying to find out the dimension of this particular writing pad. Now, if I want to know what is the exact dimension of this particular writing pad, then what I'll try to do is I'll be placing my starting end of my scale at one of the corner of this writing pad, and then I'll try to extend my scale till the end of the writing pad, and I'll try to measure the distance here. And while I am trying to measure the distance, what is going to happen is the distance what I am trying to measure, let's say for example, this is my writing pad, what I am trying to talk about. And when the scale is spread, okay, I have spread my scale from here to, scale is spread like this. And I could see that one least count dimensions I am trying to talk about. I have 1 mm dimension here, another mm dimension here. not exactly coinciding with what is called as the other end of your writing pad. Now what is happening? The distance what I have measured with the scale is not coming out to be very accurate. Why is it not coming out to be very accurate? Because of the least count problem which I have got. The least count of the scale is only 1 mm. It's not anything further less than that. I cannot measure any measurements less than that of 1 mm dimension with the help of this particular scale. So say for example, from this point to this division, the length is something 25.4 centimeter, whereas from this end to this next division, it is 25.5 centimeter. Rather, your writing pad has got a dimension which is neither 25.4 centimeter, neither 25.5 centimeter. So it is somewhere in between 25.4 centimeter to 25.5 centimeter. You are not able to accurately measure what is that particular dimension. So such kind of error, because of what is called as the least count issue, is one of the example what I can call it as your instrument error. Okay, so let's say for example, there is another possibility of what is called as your instrument error. Let's say I have while shooting, in the case of shooting, people try to look at their target because the board on which they are going to carry out their shooting in the competition. So they'll have a center circle with a target here, okay, which we call it as your bull's eye, the center point where you are supposed to be striking, so that you get more points while participating in the competition. Now, while holding your gun and while you are trying to carry out your work, okay, so when you are participating in that game and once you start firing, your bullets are not getting struck. They are not going and striking the center point, rather they are getting strike somewhere at different places. Now, why is it? What could be the possible reason? Okay, maybe the position, you might have handled that gun properly in your hands, you are holding it properly, but maybe the point which shows where to strike, when you are trying to focus, okay, your focusing lens may not be correct, or maybe your adjustment is not correct in that particular instrument. So because of which you are not able to strike your target, rather your bullets are getting striked at different places on that particular board. Though you are accurate, though you are confident, the way, the approach what you are following for targeting your target, everything is correct, but your bullets are not striking that particular place where you wanted to hit, but rather it is getting hit at different place. So those are all what we call it as your instrument errors. And likewise, we might also even come across with some other kind of error, like we call them as personal errors. Now, what do we mean by these personal errors? Let's say, for example, as a surveyor, when I am trying to carry out my survey in the field, on that particular day while carrying out the survey, my health is not good, or the climate is not very supportive. Let's say, for example, there is a heavy wind, or maybe it is very hot, or there is some rain. So what is going to happen because of various things which are psychologically or mentally disturbing the condition of the person who is carrying out the survey there? So in the process of that issues, what as a surveyor I have got while carrying out my work, so my health is not good, or maybe climate is not good, or whatever could be the reason, because of which while carrying out my survey, let's say for example, I am trying to measure the dimension by placing your chain, or maybe by placing your tape, or whatever instrument, or maybe some other instrument which I am trying to make use of for measuring some dimensions there. Okay, So instead of reading it properly like this, because of my carelessness or because of my health condition or because of something else, I might have taken readings in an improper way of holding it, or maybe improper way of vision and so on. So I might have measured the distances, and those measurements, what I have measured with inaccurate condition, those errors are nothing but we call them as your personal errors. Because of your personal reason or because of your personal conditions, you were not exactly measuring those dimensions. Okay, and you were trying to represent those dimensions after measurement. So there are certain errors in such kind of measurements, whatever you are going to be carrying out. Let's say, for example, I am trying to measure the angle between these two lines, maybe with the compass instrument or maybe with the theodolite instrument. So if I am trying to measure the angle between these two lines, say I don't have, because of some reason, I'm not very comfortable or I'm not interested in continuing my work, but my in charge is forcing me to finish off the work. So in the process, I want to finish it very fast. So while finishing my work, so I am not very accurate in taking the measurements. So my values were approximately something around 50.32 degrees, which I was supposed to be exactly getting. But I didn't exactly measure this. Rather, I was trying to say, okay, approximately 50 degrees. That so-called approximation, because of my recklessness, is giving me an error there. Actually, it was supposed to be something this, but I am measuring it as something this, which is not accurate. Okay. So those such kind of errors is what we call it as your personal errors. So these are some of those different sources of errors. What could be the possible sources because of which we come across with the errors while carrying out our surveying? Now, next to move on, how do we classify these how do we classify these errors? So whatever the errors that we have talked about, it could be your natural errors, or maybe it could be your what we call it as your instrument errors, or maybe due to what is called as your personal problems, which we call it as your personal errors. So all these different errors, what we are coming across because of various sources, how do we classify them? Okay, so classification of errors. So how do we classify these particular errors as? So one such kind of classification is nothing but I can call it as a mistake, or which otherwise can also be called as a blunder. Now, what does this blunder or a mistake mean? Let's say, for example, I carried out my survey in the field where I wanted to measure the distance between two houses in the field. So I have exactly measured it. Everything, my work, everything which I have carried out is proper. From the measurement, I got the distance to be something 50.34 meters. In the field, when I have measured the distance between those two houses, let's say I got the distance to be something 50.34 meters. But while representing, we'll have something called as a field book. Okay, we'll have a book like this, which we call it as a field book. So as a surveyor, whatever readings that we note down, whatever measurements that we take from the field, all that information has to be represented or transferred initially onto what is called as a field book. Okay, so this is what we call it as field book. And from the field book, then we transfer this particular information into the form of what is called as your map. Okay, or plan. So while measuring, you have measured the distance between those two houses accurately in the field, which is 50.34 meters, let's say. But while noting down in your field book, instead of measuring the distance from point A to point B, let's say the distance between these 2 points in the field as 50.34 meter, instead of doing this, I have noted it as 15.34 meters. I repeat, I have measured it correctly, but while reporting in my field book, while noting it down in my field book, instead of writing it as 50.34 meter, person who measured told me 50.34, I heard it as 15.34 and I have noted it 15.34 meter. Such kind of error is what we classify it as a mistake, or rather it is a big blunder Instead of noting it as 50.34 meter, you are noting simply it as 15.34 meter. So such kind of error what you are committing is what we call it as a blunder. Okay. Next kind of error, next other type of error are like systematic error. Okay. Now, what does this systematic error mean? Let's say, for example, let me go back to that case of rifle shooting. You have your target board like this, maybe with the bullseye at the center. Okay. You were supposed to target this point while carrying out your shooting there. Okay. So what has happened is, you are holding your gun properly, you are doing everything properly, but you are not able to strike your bullets at this point. Rather, all your bullets were getting struck somewhere here. I'm just randomly mentioning. It need not be only at this point, it could be anywhere. Now, what has happened? Your focusing is correct. You are able to see the target accurately through your gun, through the lens of the gun, and you are trying to shoot your bullets. But in the process, bullets are not getting struck here. Or maybe, let's say, the bullets are getting struck here. Now, why are those bullets getting struck here? There could be some physics which got involved in this. What is that physics? Let's say the effect of gravity might be there. Yes, I am focusing properly. While shooting, I am focusing my target accurately. But what has happened? Bullet has got some weight. When you shoot the bullet, according to you, it was supposed to be traveling in a perfect straight line. But due to the effect of gravity, it takes what is called as a projectile path. Its bullet is not going to be traveling like this. Rather, it travels like this. Because of the effect of gravity, bullet is getting pulled towards the center of your earth. So in the process, your bullet is not going and striking your target accurately according to your requirement. Rather, it is striking at some other point on that particular board. Okay. Such kind of error is what is called as your systematic error. And these systematic errors, whatever you come across, can be eliminated by what is called as understanding this. Yes, there is a systematic error, and you can try to prepare some mathematical models. We can talk about some mathematical models by which you can try to find out how much is the error, and we can go ahead in eliminating that particular error based on various mathematical models that you can develop, and based on some physical laws. Like if I understand law of gravity, then I can say, okay, due to the effect of law of gravity, your bullet is not exactly traveling in the horizontal path or perfect straight path, rather it is taking some curved path. So if I understand that particular law of gravity, then what I'll try to do next is, instead of focusing exactly on this target, rather I'll try to focus somewhere here. And when I try to focus somewhere here, then my bullets might at least go and strike nearer to your target where I was supposed to be striking. Okay. So such kind of error what you have is what we call it as your systematic error. Such kind of error that you are encountering is what we call it as systematic error. And the third other type of error we classify it as random errors. So what does this random errors mean? There is no mistake or there is no blunder in noting down the data. What exactly you have measured in the field, same measurement you have noted down in your field book. So you have tried to eliminate your mistake or blunder. Okay. You have taken care of all that systematic errors also to eliminate the subsequent errors. But still, once again, while carrying out your shooting, you are not striking all your bullets at this particular target. Okay, you are not trying to commit any mistake. There are no systematic errors, but still you are not able to strike all your bullets here. Rather, your bullets are getting, bullets are getting striked near to your target, but not exactly all the bullets are, most of the bullets are not striking your target exactly. Now, what could have been the problem? Okay, so it need not be systematic error, it need not be human error, it need not be your errors due to the noting down of the data. So sometimes there could be various other errors which we may or we may not be knowing also. Okay, so we may or we may not be even knowing those kind of errors, so due to which you are not able to strike your bullet onto the exact bullseye target. Okay, so such kind of error is what is called as your random error. Randomly something is happening where, because of which you are not able to strike your target. So such kind of errors are what are called as your random errors.